Hi, and welcome to Wave Revision 2. Today we're going to be looking at Young's slits and using that as a way of exploring path difference and phase difference. So, what is Young's slits? You take a laser that is monochromatic and coherent. Monochromatic just means all the same colour. Coherent means same frequency, constant phase difference. Don't worry about what constant phase difference means now, you'll know by the end of the video. And you fire it at two just little slits. So just imagine a wall with two holes in it, normally about 0.5 millimetre apart, that kind of distance. So the light is going to go through both holes. So we can imagine the light going through this hole is going to diffract because the wavelength of the light is similar to the gap. So it's going to diffract like this and sort of spread out. You know what diffraction looks like that. However, it's also going to go through this hole. So you're going to get a diffraction pattern coming out of that as well. So now what you've effectively done is you've taken this laser and sort of made it into two different lasers. And now we've got a whole bunch of waves all bouncing around here, which means you're going to get constructive and destructive interference. So if you were then to put a wall or something behind it, what you would see are these very bright red dots separated by areas with no light at all. Because here you've got constructive interference, so peaks are meeting peaks, the waves are making each other bigger, but here you've got destructive interference, peaks are meeting troughs, the waves are cancelling each other out. So you can turn one light into a series of sort of strange dots. So, how do you know if you're going to get constructive interference or destructive interference? And the answer is by looking at your phase difference and your path difference. So we'll start with path difference. Let's consider a point over here. What you would do is you would draw a line to both of the slits, and then you would work out how many wavelengths each had gone through to get to that point. Now what's neat is each wavelength, if you think about it, each wavelength distance is one full cycle. So if one wave goes one wavelength distance and the other wave goes 2, they'll actually be at exactly the same point again. If one goes 1 and one goes 101, they'll be exactly the same point, because if you're going full wavelengths, you just end up at the same cycle. So path difference doesn't care about the absolute difference. All it cares is if there's a slight integer difference. So in other words, if one went 3.5 and the other went 7, they'd have a path difference of 0.5, because this had done 3 full cycles and 0.5, and this had done 7 full cycles, so this would now be half a cycle out. If one of them had done 4.2 and the other had done 112, they'd have a path difference of 0.2, because this has done 4 full cycles and a little bit, this has done 112 cycles, so they'd still be a little bit out. So that's what path difference is. It's expressed between 0 and 1 wavelength, because if you go more than 1, you've gone through one cycle, you're back to the beginning again. So that's how we describe path difference. Moving on to phase difference. Phase difference is a measure of how out of step the two waves are, but instead of considering how far they have gone to get to that point, we will instead just look at them on a wave graph. So if we consider a wave like this, and then we consider a second wave, which starts here and goes like this, we can see these waves aren't really in sync. They are out of sync, so therefore they have a phase difference. The phase difference is how long it is between they get back to the same point. And if you look, it's constant for these two waves, because they take the same amount of time to do one sequence, i.e. they have the same frequency, their cycles take the same amount of time. The phase difference is constant. If we look at all these points, they're the same. And we can express this either in terms of time, or more commonly, and this is very strange, we do it in terms of angle, with one full cycle being 2 pi radians. So in this case, they are about 1/4 of a cycle out, so that would be pi over 2 out, maybe pi over 4, depending on how I've drawn it. It's not particularly accurate. So this is our phase difference. So we can do it in radians, or we can do it in time. These are two waves with constant phase difference, but we could just as equally have two waves where the phase difference is changing because the two waves themselves have different frequencies. Consider this wave and this wave, which is going twice as fast. So this one has twice the frequency of this one. At the beginning, they don't have any phase difference because they're exactly the same point in the cycle. So the phase difference here is 0. At this point here, this one's going down at the point where this one's at the top. So the phase difference, they're out by pi over 2. They're half as much out of phase as you can possibly be. At this point, they couldn't be more out of phase because this one's going down and this one's going up. They're at exactly opposite points on the cycle. So they've got a phase difference of pi. But note, once they've gone past this phase difference of pi, they start to get back into phase and get fully in phase by the end. With again, at this point, phase difference of pi over 2, this point phase difference of 0. Now this should tell you something interesting, which is the maximum phase difference you can possibly have is pi. Because if you start to go further out of phase, you actually start to sink back up again. So pi is when you're going in completely opposite directions. Anything less than that means you're doing something where you're a bit out, and if it's 0, you're doing exactly the same thing. So there you go. There's a question underneath. I'll see you next week.